In this video, we continue with our concepts discussion of Chapter 2. We're going to finish up Chapter 2 and focus on elements and their classifications. We're going to look at something called the periodic table. The periodic table is an arrangement of the known elements, and they're organized based on their chemical and physical properties. Then we'll look at compounds and some classification schemes for them. We'll finish up looking at chemical formulas, chemical naming, and we'll have an introduction into molecular masses for compounds. So we now have an understanding of the basic structure of elements and atoms. And now we'll take a look at how we designate an element. So the box in the center, this is how we designate an element. Each element has an atomic symbol. In this case, it's shown as X. There is no element X, but typically it's a 1 or 2 letter designator. And that 1 or 2 letter designator identifies each element in the periodic table. In the upper left-hand corner, we have the mass number. The mass number is the number of protons in the element plus the number of neutrons for that particular atom. And in the lower left-hand corner, we have the atomic number. P plus is the number of protons. The atomic number is the defining characteristic for an element. If you know the element, you know the number of protons. If you know the number of protons, you know the number of you know the element that you're looking at. That is the defining characteristic. And so while it's very important, we typically don't write down Z in the lower left-hand corner, because if we know the atomic symbol, we know the atomic number, and vice versa. So the atomic number simply becomes redundant once we have the symbol. But here on the first couple of slides, we will see the atomic number written. It will not generally be done going forward throughout the semester, and in subsequent studies, your subsequent scientific work, you won't see that. So A is the mass number. That's the number of protons plus the number of neutrons. Z is the atomic number, the number of protons. And X is the symbol. Now, an isotope is an atom of an element. And of course, it will have the same number of protons, but a differing number of neutrons. And a good example of this is uranium. Uranium is an element. It's a metal. It's an actinide at the bottom of the periodic table. And uranium atoms have 92 protons in them. There are two very common isotopes of uranium, uranium-235 and uranium-238. Uranium-235 has 235 protons plus neutrons. And so you can see you have 92 protons and 143 neutrons. Uranium-238 has 92 protons again and 146 neutrons. Typically, this will just be written as U-235 or U-238. So U-235 and U-238 are two isotopes of uranium. They have the same atomic number, but a different mass number. Now, we're going to come across something very soon, and it's the atomic mass for an element. Typically, there'll be multiple isotopes for an element, and if you take a naturally occurring sample of that element, they'll tend to have the same distribution of the isotopes by mass fraction. So we have an example here, silver. Silver has two very common isotopes, silver 107 and silver 109. There are some man-made isotopes which are trace level or radioactive. They're not particularly important. But silver has two important and commonly occurring isotopes. And the abundances are shown in this problem. Approximately 51.8% is the abundance of silver 107, and 48.1%, 48.2 if we round it, for silver 109. Now, when we have a sample of silver, the atomic mass can be determined by coming up with a weighted mean for the various isotopes. And the weighted mean equation is shown in the lower left-hand corner. The weighted mean is equal to the sum of each individual mass value, that would be the x sub I value, multiplied by the fraction of that particular isotope, and that's W sub I. So for this case, for example, silver 107, the WI value would be 0.5184. So we don't write it as a percentage, we write it as a fractional value. And the sum of all the W sub i's will equal 1. Each W sub I then is multiplied by the particular mass for that isotope. And these then are added to give the overall atomic mass. And if you do this calculation, you will see that you'll get a number, and that number is the same as what you see in the periodic table, which we'll approach in just a moment. So now that we have an understanding, we can go back and do a reassessment of Dalton's atomic theory. And the letters in blue are the modern version, or the modern articulation of what Dalton had expressed. First, all matter is composed of atoms. The atom is truly the smallest body that retains the unique identity of the element. And while the properties may change a little bit, we will see when we look at nanotechnology a little bit, but it still tells us, what gives us the unique identity of the element. Number two, atoms of one element cannot be converted into atoms of another element in a chemical reaction. Elements can only be converted into other elements in nuclear processes. Number three, all atoms of an element have the same number of protons and electrons, which determines the chemical behavior of the element. Now, this is atoms of an element in an elemental sample. Elements in compounds can lose or gain electrons, so the most important factor is the number of protons. That defines an atom of an element. Isotopes of an element differ in the number of neutrons and thus in mass number. A sample of an element is treated as though its atoms have an average mass, and that's averaged across all the isotopes. And finally, compounds are formed by the chemical combination of two or more elements in specific ratios. That's still true, though we think about the combination not based on mass so much as amount of material. And we'll look at molar amounts when we move on to chapter 3. And here are three micrographs helping us to actually see the discreteness of matter. In the upper left-hand corner is the green, kind of greenish figure. These are some semiconductor nanoparticles that were produced in our labs a few years ago. It's a lead sulfide, which is a narrow bandgap binary semiconductor. And you can see dark ridges. Those dark ridges occur because of what we call lattice planes. That is, arrangements of atoms within the crystal. So you can see discreteness in the matter. There are spaces in between the atoms that are relatively empty and have less mass in them. In the upper right-hand corner, this is another sample from our lab. This is semiconductor nanowires. It's something called Sri-Lankite. It's a titanium zirconium oxide. It's a ternary semiconductor. And the darkest lines in there correspond to zirconium atoms in the lattice. And the lighter bands are the titanium atoms. And in the lower right-hand corner, this is an atomic force micrograph of a gold sample, and you can see images of individual gold atoms on the surface. So we have the final fact that we now know to be true, and we can observe and have kind of verified with a variety of different methods. Matter has discreteness, that is, quantization. It exists in localized packets. And while that seems like something that's commonly accepted nowadays, this is an extremely important fact. Returning to elements, it turns out that there's approximately 90 naturally occurring elements. That includes a couple of radioactive elements, so sometimes you'll see a fewer number for elements that are not particularly stable, but as they occur on Earth, naturally occurring right now, there's approximately 90 elements. You'll look in your periodic table in your textbook, or if you go other places, you'll see a larger number of elements. Those other elements that we see on that table, and another approximately 35 plus elements, those are man-made elements that exist only in trace quantities. Now we can contrast elements with compounds, like we talked about earlier. Compounds are combinations of elements. There are many more compounds that are known. Currently, there's over 100 million known compounds, and this number is increasing by approximately 5 million per year, and it has been accelerating over the last 40 years as worldwide chemists and material scientists have been developing new and improved materials for a variety of applications. Now, as far as the elements are concerned, we have something we call the periodic table. The periodic table is an arrangement or a grouping of the elements. And we're going to focus on the naturally occurring elements, though the man-made elements will also be listed. One of the questions you might ask is, why is the periodic table organized the way it is organized? And we'll see in just a moment how it's organized. The key to remember is the elements are organized based on repeating properties as a function of increasing atomic number. And so we'll see that the elements that have similar chemical and physical properties are grouped together, and you get this repeating order as the atomic number increases. This is a picture of Dmitry Mendeleev's first periodic table. Dmitry Mendeleev is credited with coming up with the first effective periodic table. Last year was the 100th anniversary of his periodic table. This is arguably the most important discovery in chemistry ever. He's arranged the elements according to repeating properties as a function of, at that time, what was known as the atomic mass of the system. He even predicted the existence of certain elements that had not yet been discovered based on his repeating properties. So it's a very important piece of work. A little side point, Mendeleev was never given a Nobel Prize in chemistry. Mendeleev was a Russian, and Sweden, the Swedes may not have been interested in giving him a Nobel Prize, but also he was more of an industrial chemist and probably got a little bit less respect from the academics. But clearly, he was an extremely important scientist and brilliant chemist. This is the modern periodic table, and this is what you will be working with this semester and likely in your future career. Each box on this table represents a single element. In the center of the box is either one or two letters. That is the chemical symbol for the element. So in the upper right-hand yellow box, you see H. That's hydrogen. Above the letter is the atomic number. So for hydrogen, it's 1. And below the symbol is the atomic mass. That's the isotope averaged molar mass for the system, which we'll use a lot this semester. So we start off with hydrogen. As we move to the right, we see helium in the first row. Then we come back to the second row. Lithium is our third element. That's got 3 protons, beryllium, boron, carbon, and so forth. And you can see, as we read from left to right and then go down a row, the atomic number increases monotonically. The important key here is each column of elements represents a family of elements. Sometimes we term this a group. These groups have similar chemical properties. So each column individually is very important to recognize. Now, sometimes we'll group columns together. So, for example, on the right-hand side, you see main group elements. Those are the main group metals. In the middle, you see transition metals. On the right-hand side, you see the main group elements. They're grouped together, and that is one similar grouping. But the most important one is each column represents a group of elements. At the very bottom, you see the inner transition elements. This could have been stuck inside, but then the periodic table will become quite wide. This is a break, and so you can see element number 57, that's lanthanum. And then right next to it is hafnium, which is 72. In between that goes the lanthanides. So that's row 6. And then the actinides would fill into row 7 between actinium and rutherfordium. So it's important that you should learn the names and symbols of the first 3 rows of the periodic table, plus the first row of transition metals. Let's go back and look at this. Those first 3 rows, and really the 4th row has a lot of important elements in it too. You will see these elements throughout your work. You're taking a chemistry course, presumably because this is, in large part because this is important for your particular career discipline that you're working on, whether it's biomedical sciences or health sciences or engineering or earth sciences. It's an important discipline, and you will come across chemical compounds and elements frequently in your studies. So it's important to know the symbols. And while that seems somewhat tedious, it really is useful to learn this. And there's probably, 24 elements that you'll come across very frequently, and you should know the symbols and their names. So we have repeating properties. Each group has a unique set of properties. And here's a table where I've written down the group and their common name. So the leftmost group, group 1, the first column, those are the alkali metals. And we'll see later on they tend to all form monovalent cations. They're all very violently reactive with water. And when you put them in water, they form alkali. They form basic solution, an alkaline solution, like red metal lye. The second column, group 2, is the alkaline earth metals. The phrase earth typically means it's found in the earth, it's found in soil. But those are also alkyl materials, and they all tend to have similar properties. Now, coming from the other side, group 18, that's the rightmost column in the periodic table. Those are the noble gases. They used to be called the inert gases, but they're not truly inert. But they are noble. They're an unreactive group of elements. They exist as monatomic gases and pretty much chemically unreactive. Group 17, that's the second column from the right. Those are called the halogens. There's a bunch of very important halogens. You've got halogens in your body. They're important nutrients. They're ubiquitous in the environment. They're very important industrially. So we'll spend a lot of time with the halogens. They tend to form anions with a -1 charge. And then group 16 is the third rightmost, and that's sometimes called the chalcogens. That's not a real common name, but they're called chalcogens. In group 15, you'll sometimes see the phrase pnictogens. Groups 3 through 12 in the middle, those are the transition metals. Each column of transition metal tends to form similar sorts of compounds, and the block as a whole, groups 3 through 12, tends to have similar chemistry as well. And the lowest block, that's the lanthanides and the actinides, they tend to have similar chemistry. Now that's a row, and those rows tend to be fairly similar in terms of their properties. The lanthanides are sometimes called the rare earths. These are very technologically important elements. And in fact, you have some in your hand right now. If you're working on a computer, you've got some lanthanides in your computer. They play very important roles in technology, and as the name rare would imply, they're actually somewhat rare. Now, some of them are actually abundant, but some of them are not that common, and that's why there's a lot of concern about getting control of lanthanide deposits. Another classification scheme is based on the overall properties of the elements. And there are three groupings of elements. We have metals, metalloids, and nonmetals. So if you look in the upper right-hand corner, you see a shadow of the periodic table. There's no elements put in. But the gray region represents the metals. The yellow region represents the nonmetals. And the green region is the metalloids. You can see pictures of them here. The metals look similar to the metalloids, but the metalloids can be very hard materials. So metals are a little bit different. They tend to be more softer and malleable. And the nonmetals can be solids, liquids, or gases. So in this broad classification scheme, metals as a group are electrically and thermally conductive materials. That's why when you touch a metal, it feels cool. It conducts the heat away from your hand. Metals are stretchy, though they can be hard materials. They're also tough and stretchy, so they can be malleable and ductile. And we'll see an atomic explanation later in the semester to describe why this occurs. Metals tend to be electropositive. That means they form positive ions in their compounds. They give up electrons. They can be reducing agents. We'll see what that means later. Metals are solids excepting for one element, and that is mercury. They tend to form oxides that are alkaline. Nonmetals are generally non-conductive, both thermally and electrically, and there are two exceptions. One is graphite. Graphite is an elemental form of carbon that is an electrical conductor, and diamond is an elemental form of carbon that is a thermal conductor. Diamond is an electrical insulator but thermal conductor, which makes it important for technological applications. Nonmetals tend to be brittle when they are solid form. They tend to be electronegative, that is, they form negative ions in their compounds. And there are gases, liquids, and solids. The gases are the group 18 elements, the noble gases: hydrogen, nitrogen, oxygen, fluorine, and chlorine. And bromine is the only liquid nonmetal. So there are two liquid elements at room temperature, mercury and bromine. Bromine is a nonmetal, mercury is a metal. The nonmetals tend to form acidic oxides in their oxide compounds. The metalloids are a small band of elements between the metals and nonmetals, and sometimes they're called the semimetals because they're halfway between metals and nonmetals. They're semiconductors, and we'll see if we have time when we get to chapter 12, we'll see what that means. They can gain or lose electrons in their reactions. They're all solids, and they form amphoteric oxides. An amphoteric compound is something that's both an acid and a base. That's our classification of elements. Let's move on to chemical compounds now. The first group of compounds we'll look at are ionic compounds. Ionic compounds come about when you take a metal and a nonmetal and react them together. Metals, as we saw, are electropositive. They tend to lose electrons. Nonmetals tend to gain the electrons. An ionic compound is formed when the metal gives up electrons to the nonmetal, and you form two ions, a cation, that is with a plus charge, and an anion with a minus charge, and now these ions attract one another and positive and opposites attract, so the positive and negative attract and form a crystal lattice. So here, this is a picture, and it looks similar to what we looked at in our previous concepts video. Sodium metal plus chlorine gas comes together to form sodium chloride. And that sodium chloride crystal is shown in the lower right-hand corner. Now, all metals don't form ions with just a single charge. Some have more than one charge. And there are many nonmetals that form ions that have more than one negative charge. And this is the trend, and this is one you will need to know because this will be important for you when you go to predict compounds, so you should know this table. Group 1, those elements, the alkali metals, they tend to lose one electron to form a monocation. That is a metal with one charge, one plus charge. Group 2 tends to lose 2 electrons to form a dication, or a metal with 2 plus charges. Groups 3 and 13, they often and generally lose 3 electrons to form a metal with 3 charges on it. You don't see metals or elements commonly with more than 3 charges on them because that becomes unstable. We'll see formal oxidation states that are higher, but generally the charges are limited to 3. Now, coming from the left-hand side of the periodic, or the right-hand side of the periodic table, is group 17. So group 18 is unreactive. It's always got a 0 charge. It doesn't gain or lose electrons. But elements in group 17, that's the second column from the right-hand side, that's the halogens, they tend to gain 1 electron to form a monoanion, like X minus. Group 16 tends to gain 2 electrons to form the dianion form. And there are some compounds in group 15 where they gain 3 electrons. And that's not a general rule, but in a number of compounds they do gain 3 electrons. And we'll see examples of that. Now, once you form your ionic compound, the strength of the bond that forms depends on the charges that are produced to make the compound. And this figure illustrates that. As the number of charges on each ion increases, the attraction increases, and that means the bond is stronger. And as the ion gets bigger in size, the bonding gets weaker. We'll look at this in detail when we get to chapter 9 and look at ionic bonding and lattice energy. This figure simply shows what we already wrote in the earlier table. Group 18, that is the noble gases, helium, neon, argon, krypton, and xenon, are at the center of the picture. Those are unreactive systems because they're very stable. And it turns out that the elements nearby them in the periodic table tend to either lose or gain electrons to reach that stable state so that they will have the same number of electrons as the nearest noble gas. So, for example, lithium, which is atomic number 3, tends to lose 1 electron, so it only has 2 electrons, and that mimics the electron structure of helium. You can see this happens for similar elements. Sodium, Na, plus tends to lose an electron to be like neon. Magnesium, Mg, tends to lose 2 electrons to be like neon. And aluminum tends to lose 3 electrons, Al, to be like neon. Correspondingly, fluorine will gain 1 electron to have the same number of electrons as neon. Oxygen gains 2 electrons. Nitrogen gains 3. This sample problem is one you should go through. This basically articulates what we saw in that earlier table that we had where each group with the corresponding charge is shown. So for iodine, that's group 17. You expect it to gain 1 electron. Calcium is in group 2, tends to lose 2 electrons. And aluminum is in group 13, or group 3A, and tends to lose 3 electrons. That's ionic bonding. There's another type of bonding that occurs between atoms, and this occurs commonly for atoms that are identical, but it also occurs with nonmetals in general. So when we have two nonmetal atoms come together, they will tend to share their electrons. And in that sharing process, that pulls the atoms together and creates a cohesive force to stabilize the system, and that's how compounds are produced. This is shown here for two hydrogen atoms. Each has 1 proton and 1 electron. As they come together, they share electrons. We'll look at this in much more detail later on. We can classify compounds into 2 groups. The first group is the ionic compounds, as we saw. This is when I combine a metal with a nonmetal. Ionic compounds tend to be hard materials, like salt. They tend to be brittle, so they fracture when you hit them. They have high melting points. They're somewhat water soluble. Some of them are very water soluble. When they dissolve, they form electrolyte solutions. The solids themselves are non-conductive, but in the molten state, they are conductive. Covalent compounds usually occur when we have 2 nonmetals interacting to form a compound. Covalent compounds tend to have lower melting points. They can be either solid, liquid, or gas at room temperature. They widely vary in their solubility. They're generally non-conductive in their solutions, though acidic or basic systems can be electrolytic. And they tend to have non-conductive solids. As we saw before, the molecule is the basic unit of compound, or an element where the smallest unit is a molecular unit. And a molecule is where we have 2 or more atoms bonded by sharing electrons. Most covalent substances consist of molecules. We'll see some covalent solids later on, covalent network solids, which are special cases. Ions are individual atoms or a covalently bonded group of atoms that has an overall net charge. Ionic compounds are not in themselves molecules, but they can be involved in forming molecular systems. Polyatomic ions are a mix of covalent bonds to produce a system that is overall has a net charge, or it's ionic. Now, these are the elements that occur as molecules, individual molecules, and they're covalently bonded. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are diatomic molecules. Sulfur and selenium are octatomic, that is, there's 8 atoms in their individual units. Sulfur forms ring systems, so there is a group of 8 atoms in a ring. Phosphorus, in one of its allotropic forms, is P4. Here's an illustration of a typical polyatomic ion. We have atoms that are covalently bonded together. So for carbonate, as an example, you have 1 carbon atom and 3 oxygen atoms. The carbon atom is at the center, and the 3 oxygen atoms on the outside, and it has a net -2 charge. You cannot get a pure sample of carbonate, but carbonate exists in compounds like, for example, calcium carbonate. Polyatomic ion exists of 2 or more atoms covalently bonded together with a net overall charge. Next, we're going to look at chemical formulas, and we'll talk about naming as we go forward. We need to be able to, we know symbols for elements, and you'll learn the names for a number of elements. Naming compounds is a bit more complex. Chemical formulas consist of the element symbol with numerical subscripts to indicate the number of that atom in the smallest unit of the substance, whether that's a molecule or whether it's the smallest whole number ratio for an ionic compound. So let's look at naming binary ionic compounds. Binary means that there's two elements involved. And since it's an ionic compound, one element will be positively charged and the other will be negatively charged. The positively charged ion is called a cation, and that is named first. The negatively charged element in the binary ionic compound is the anion, and that is listed second. In the binary ionic compound, both the cation and the anion are monatomic. The name of the cation is the same as the name of the metal. So, for example, sodium chloride, sodium is the metal, we simply use that name. The anion, however, is not written as, for example, sodium chlorine, it's chloride. You use the suffix IDE to the root of the nonmetal name. So, for example, calcium and bromine. Calcium is a metal, bromine is a nonmetal. We form calcium bromide. Now, as we look, here are some common charge states. You can see that we have charge states like +1 for the group 1 elements, +2 for group 2, +3 for group 3. But there are some elements, for example, silver, which is not in group 1, which tends to form a +1 charge. And there are elements like cadmium, which is not in group 2, which forms a +2 charge. And then we have the anions. Group 17 anions form -1, 16 -2, 15 -3. So nitride, or right below it is phosphide in the periodic table. Now, as we look at the transition metal, or in the transition metals in the middle, we see that some of them will have two possible charge states. In fact, some may have more than two, but two tends to be more common than higher numbers. So now, if I'm combining, for example, let's say I take iron and I combine that with chlorine, I would form an iron chloride. But there are two different iron chlorides. The iron chloride with a +2 charge needs 2 chlorines attached to it. The iron with the +3 charge needs 3 chlorines attached to it to make an electrically neutral system. So if we're going to name this compound, we have to somehow indicate that. And the way we indicate it is not by the number of atoms, but by the charge state on the system. So now the first group we'll look at are ones that have only a single charge state. So let's go back to figure 217. Group 1 and group 2 always has the same charge state. Group 1 is +1, group 2 is +2. In group 13 with aluminum, it's always +3. So when we name those compounds, we simply write the metal with the nonmetal because there's no ambiguity. And we'll look at examples of this in our subsequent video, but this one example here, magnesium and nitrogen, there's one atom of magnesium and one atom of nitrogen. Magnesium tends to have a +2 charge, nitrogen a +3. The system needs to be overall charge of 0. So I'll have magnesium nitride, and the formula will be Mg3N2. Iodine and cadmium. Cadmium is +2. Cadmium iodide, that's a case where there's only one charge state. Strontium and fluorine, likewise. Strontium fluoride, and sulfur and cesium. So now if we want to write down the formulas, we did magnesium nitride, Mg3N2. Right? What about cadmium iodide? Cadmium tends to form a 2+ charge. Iodide is a -1, so we're going to need 2 iodines for each cadmium to make it electrically neutral. And we see that here. Strontium fluoride, strontium tends to form a +2, fluorine a -1, so we'll need SrF2. And finally, cesium sulfide. Cesium forms a +1, sulfur has a -2, so we'll need CS2S. Now, for metals that have more than one charge state, for example, iron halfway down, we will simply write the charge state in parentheses when we write out the compound name. So this is the case: chromium, cobalt, copper, iron, lead, mercury, tin, and many other transition metals. We simply write the charge state in parentheses. That's sometimes called stock notation. There are common names as well. The OUS refers to the lower charge state. IC refers to the higher charge state. So for tin 2 fluoride, that's going to be SnF2. For Cri3, that's chromium 3 iodide. Ferric oxide, that would, for our case, be iron 2 oxide, FeO, and cobalt 2 sulfide. And you can work through and prove these to yourself. Now, polyatomic ions, as we saw earlier, they're a group of atoms bound together. Polyatomic ions tend to be given a common name that we simply use. There are two common polyatomic cations, that is ammonium ion and hydronium ion. That's NH4 plus and H3O plus. You should know all the names and formulas in this table, though you will have access to it on an exam, but you will use these constantly, and so it's important to remember these because it'll make your work a lot easier. And you can see there's a variety of anions here: acetate, cyanide, hydroxide, and so forth. This is not a complete table. There's a more complete table in your text, and we will come across some other ones as we go throughout the semester. There's a special group that you need to learn, and those are called the oxoanions. Oxoanions are where you take one nonmetal and surround it with a group of oxygen atoms, and it has a net charge. And oxoanions typically have either 1, 2, 3, or 4 oxygen atoms on them. And they very commonly have a -1 charge, but there are ones that have higher charges, like -2 and -3 for groups 16 and 15. The way these are named is you take the root name for the central atom, the non-oxygen atom, and that's your root. And you simply identify the number of oxygen atoms based on this table as either ATE or ITE suffix, and in certain cases you'll add PER or hypo as a prefix. So for chlorine, for example, we have perchlorate, ClO4 minus, chlorate, ClO3 minus, chlorite, ClO2 minus, or hypochlorite, ClO minus. There are cases where there's only 2 versions, and if there's only 2 versions, you simply use the intermediate states, or one version is very often as the ATE. Now we're going to come across covalent compounds, and covalent compounds, these are simply identified with a prefix, and that tells us how many atoms are involved. So you should know this. You'll use these prefixes throughout this course and in organic chemistry and other places as well. So if there's one atom, it's mono. So for example, 1 oxygen would be monoxide, 2 would be di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. So here's a chance to name compounds with polyatomic ions. Now let's take the first one, and you should do these problems on your own. But take the first one. You have iron. You can see Fe. You remember that iron has two possible charge states, so you need to indicate what that charge state is. How could we discern that here? Well, we look at the counter ion, the negatively charged ion, ClO4. And if you remember a few slides up, ClO4 is perchlorate that has a -1 charge. Since we have two -1 charge species, iron must have a +2 on it. So that will be iron 2 perchlorate. You can go through and do sodium sulfite and the barium hydroxide octahydrate yourself. Next, we're going to name acids. There's one simple group of acids called the binary acids. We'll learn what acids are later on, but a binary acid is a solution. It's a binary compound with only two elements, and one of the elements is hydrogen. The other one is a nonmetal. Binary acids form when these compounds dissolve in water, and the way we name them is given right below. We write the prefix hydro, we put the anion root name, then we add IC suffix. So then, for example, chlorine would be hydrochloric, bromine would be hydrobromic, sulfur would be hydrosulfuric, and then we add the word acid at the end. So for HCl, we have hydrochloric acid. The oxoacid names are similar to the name, they're derived from the oxoanion name, except we have two suffix changes. If we have an anion that's an ATE, so for example, chlorate would simply become the IC acid, so that would become chloric acid. Ite, so for example, if we had chlorite, that becomes the OUS acid. So in this case, that will be chlorous acid. The oxoanions that have the hypo and per prefixes, those are retained. So BrO4 minus, that would be perbromate. Then HBrO4, and the H, of course, has a +1 on it, so this makes it net neutral. HBO4 becomes perbromic acid. If it was chlorine, it would be perchloric acid. IO2 minus is iodite, so HiO2 is iodous acid. We'll let you go through and do this practice problem on your own. You should pause and solve this yourself. So now we'll look at naming binary covalent compounds. This is where we have two nonmetals. We've looked at this before. The binary covalent compounds, the element with the lower group number in the periodic table is first. It's either the lower group number, so that, for example, group 15 would be listed before group 16. But if they're both in the same group, then you use the element that is lower down in the periodic table. And you simply add IDE to the second element. And you put the prefix to indicate the number of each atom. So for example, carbon disulfide, you've got carbon, and you have sulfur, and it's disulfide, so there's two sulfurs, so you have CS2. Mono is usually left off, except in some special cases like carbon monoxide. So we wouldn't write monocarbon disulfide. We simply write carbon disulfide. You can do the same thing for PCl5, solve that one, and solve letter C, 2 nitrogen atoms and 4 oxygen atoms, write out the formula for that, and write out the name. Pause the video and do that. The last thing we'll look at are straight chain alkanes. These are organic compounds. So this is the only class of organic compounds we'll look at this year, but you'll do a lot with this later on. We're going to start off with the simplest group, and these are covalent compounds. They're alkanes. An alkane is a carbon and a hydrogen group of atoms combined together. And we simply write ANE with an appropriate prefix. So for example, carbon with 4 hydrogens is methane, 2 carbons with 6 hydrogens is ethane, and so forth. You should know all of the compounds in this table. Molecular mass is simply the sum of the atomic masses of all of the atoms in a given compound. And we're writing this out now, and you'll do a little bit of homework on ALEKS in Chapter 2 on this. But when we get on to Chapter 3, we'll do this in earnest, and we'll spend a lot of time doing this. Here's a chance for you to practice doing this, so you should pause the video and solve these problems now. Our last slide today in this video is different ways of representing compounds. We can write out the molecular formula, but we can also draw out stick figures or space filling models, and we'll spend a lot of time doing this later in the semester. But this is just to show you what it will look like in the future. That concludes Chapter 2 concepts videos. Next up, we will do a mechanics video.